In this video, we will install the new Unity input system and then use it to let the user control the camera through a series of input actions we define. Let's first open up the package manager and install the input system package. Once the package has finished installing, it'll ask you if you want to replace the old input system because this requires the editor to be restarted. Click Yes, and the editor will start automatically. Now that we have the package installed, we can begin by creating a new folder where we can place the input system assets we will need. We will name this folder Input. Let's open our project settings window under the Edit menu. Here we can see that the editor is warning us that the old input manager has been disabled because we have selected the new input system for our project. If we look at the Input System package menu, we will see a button that allows us to generate the input system asset we need to get started. After we have generated this asset, let's move it into our new input folder. Let's go into the input folder, and now we want to create an input actions asset that we will use to define the input controls for our user camera. We'll name it User Actions. Look at the new input actions asset in the inspector. You will see there is a box we can check so that Unity will automatically generate the input actions script we need based on this asset. Select this box, then click on the button that says Edit Asset. We are now presented with a window that allows us to define all of the input actions we will need to control our camera. An input action is a way for us to separate things we want the user to be able to do from the details about which input devices will trigger those actions. For instance, we want the user to be able to zoom the camera's view, but we might want this action to be triggered in different ways depending on how the user is running our application. If they are on a desktop computer, we might want them to be able to zoom using the keyboard or the mouse wheel, but if they are on a tablet or a phone, we might want them to be able to zoom using a pinch gesture on the touchscreen. And later, we might expand our application into virtual or augmented reality, and then we want our user to be able to zoom using a gesture with their hand. The new input system ensures that we can use one input action called zoom throughout this whole development process, and we will simply update which device triggers this action. This will become much more clear once we begin defining our input actions. Let's start by defining an action map for our user. This is a name for a collection of input actions. Let's call our action map User. Now, let's update the properties of the new action that Unity created for us to match our needs. First, let's rename the action to Pan and expand the action to see the bindings inside. Each binding is a way for us to connect this action to a specific device that can trigger the action. Each action can have multiple bindings that are triggered by different input devices. We want this action to control the pan of the user camera. This action will allow the user to move the camera in all four directions over the map. So we want this action to produce a 2D vector like a joystick or a directional pad on a controller. In order to access the 2D vector option, we first need to set our action type to value. Then we can choose vector 2 for the control type. Now we need to delete the simple empty binding that already exists, and we can replace it with an up, down, left, right composite binding that allows us to define an input path for all four directions. We can now go through each direction and assign a key to each using the path field. We are going to use the traditional WASD mapping that is common across many computer games. This completes our pan action for now. Let's also define our zoom action. Create a new action, then delete the existing binding and replace it with a positive-negative binding. We do not need to change the action type for this option. We will map this binding to the Q and E keys. We're also going to change the control type of our pan action to D-pad, because this more accurately represents our binding than a generic 2D vector binding. The main difference is that a D-pad is discrete. It is either on or off, just like a keyboard key, whereas a 2D vector could have a continuous value between 0 and 1. This completes our action map for now. We can choose Save Asset at the top, and then our input action script will be generated for us. Unfortunately, it looks like the name we chose conflicts with the naming scheme used when generating our input actions script. So we're simply going to delete the generated script and then change the name of our asset to User Input Actions to avoid this conflict. Now that we've cleared up that error, our action map is ready to use. Let's open up our user script again, and we can begin connecting these input actions to our camera. The first thing we're going to do is introduce a scriptable object that will store settings related to the rendering of our simulation. Let's start by creating a new folder to hold our scriptable object scripts. Then we'll create a new script called Render Settings in this folder. Let's open this script and set it up as a scriptable object. We will use the scriptable object class to define what our asset should look like. Then we will use the Create menu to make an instance of our asset. Once again, it will be helpful to see this in action. To set up our scriptable object, we will first have it inherit from the scriptable object class, and then we will define a Create Asset menu attribute for our class, which will define how the scriptable object appears in the Unity Editor Create menu. The Create Asset menu attribute has a file name property that lets us choose the default file name that will be given to any new asset we create of this type. And it also has a property called Menu Name that lets us define how it'll show up in the Unity Editor's Create menu. For the file name property, we're going to use Render Settings in camel case, and for the menu name property, we will use Render Settings as 2 words. Now we're going to define a series of public variables that will serve as settings for our rendering system. We can use a header attribute within the class to create a title header that we will see when viewing a Render Settings object in the Unity Inspector. We are going to use this attribute to define a camera section, and then we will define a series of variables related to the user camera. We are also going to use a space attribute to put some room between the variables to help group them into logical sections. These attributes and properties will make more sense once we look at them in the inspector and begin using them to set up our user camera. Now that we've finished the template class for our Render Settings asset, let's create a folder where we can put our new asset. We will put this folder in the Resources folder so that we are able to load the settings asset from our application while it is running. We will call this new folder Settings. Let's open this folder, and now we can right-click to bring up the Create menu, where we will find that Unity has added a new menu option that matches the menu name property we defined in our scriptable object. Let's create a new Render Settings object and accept the default file name we chose. Now, if you'll look at the inspector, we can finally see everything we set up in the template script. You can see the camera header in bold above the fields, and you can see the spaces we placed between some of the variables. You can also see that we are able to edit the initial values while inspecting this asset. This is one of the most important advantages of using a scriptable object. We are able to change these values even while the application is running, and the changes will be retained in the asset even after we stop running the application. We can now return to our user script and begin using these settings to control the camera. The first thing we'll do is get a reference to the new Render Settings asset we just created. Remember, we placed it in the Resources folder so that it would be available while our application was running. We will define a private Render Settings variable, and then in the awake method, we will use the load method from the resources namespace to get the reference. Let's define some private instance variables that can store some of these settings for our camera to use in the script. We could actually have the camera directly access the render settings objects for these values. In that case, if we made changes to the settings asset while the application was running, it would automatically affect our user camera. This may be exactly what you want in some cases, but for our purposes, these settings are only going to act as initial default values. We might eventually allow the user to change these private variables while the application is running, and then we can let them restore the camera settings to default by getting them from the render settings asset again. It all depends on how you want to use the information in your application. Now we have the pan speed and the zoom speeds stored in variables that we can use while updating our camera. Let's also set the initial zoom settings for our camera by defining the orthographic size. This is the size of the viewing rectangle for an orthographic camera. If we increase the size of this rectangle, then it will zoom out our view of the map, and if we decrease the size, it'll zoom in. We can now begin getting references to the input actions that we set up in the beginning of this video. These actions will give us access to the input values that we will use to update our camera. First, we'll define a reference to the user input actions script so that we can instantiate a new version of this component for our application. This will initialize the input actions map so that we can begin getting input values. Then we will create a reference to each of the input actions we defined in the action map for our user. We will be able to use these actions to read the actual input values. Now we can move to the awake method to set up these variables. First, we'll instantiate the user input actions script, then we'll get each of the input actions from this new object. You can see the user input actions object contains the actions inside of a user action map object just like how we define them in the editor. We also want to enable these actions whenever this script is enabled and disable them whenever this script is disabled in the scene. We will introduce the onEnable and onDisable Unity callback methods in order to do this. Otherwise, the input system would continue to monitor these actions for input when they were not needed. Now we're ready to use the actions in order to update the user camera. We will define two private methods called updatePan and updateZoom in order to handle the logic for each of these situations. We will call them both in the Unity update callback. To update the camera's pan, we will first read the vector2 value from the pan input action. Then we will calculate how far the camera should be panned by multiplying this input value by the pan speed we have chosen in our render settings. Notice, we are converting the value to a vector3 in this step because that will match the camera's position. In order to get a nice smooth movement of our camera, we will then use a linear interpolation to move the camera from its current position to a position offset by this new displacement. The vector3 class contains a linear interpolation method that interpolates vectors. A linear interpolation simply moves between two values using a straight line to connect them. The third argument to the method is the amount we want to move along this line. We are using the delta time to ensure we move a small amount that is proportionate to the amount of time that has passed since the last frame. That's all we need to do in order to update the camera's pan. Let's run the application and test it out. As you can see, we are now able to move the camera around the map. Let's go back and finish the update zoom method using a very similar approach. The zoom will be updated with the same technique we used on the pan, but this time it is a one-dimensional value rather than a vector value. We'll start by getting the input value from the zoom action. This time we are getting a single float value, and then we are multiplying that value by the zoom speed we set up in our render settings. We then use the linear interpolation method from the math float namespace to smoothly change the zoom by slightly displacing the camera's orthographic size by the delta time. We are also going to clamp this value so that the user is not able to zoom the camera to extreme values, because that might ruin their experience. The math library also has a clamp method that takes the value we want to clamp as the first argument, and then the minimum and maximum values we want to clamp the value between as the next two arguments. We then use this new clamped value to replace the interpolated value for the orthographic size. This ensures the camera will zoom smoothly but stop whenever it hits our max zoom or min zoom values from our render settings. We now have everything we need to update the camera's zoom. Let's test the application again and make sure all of the camera controls are working together correctly. You can now see that the camera has its full functionality. We can pan the camera with WASD, and we can also zoom the view with Q and E. But we are going to open up our Input Actions editor and make one small change. It feels more natural for me if Q zooms out and E zooms in. So we're going to swap those keys in our action map. To do this, we simply expand the QE binding again, and then change the paths we set for the negative and positive fields. Let's save the asset and then test our camera controls one more time to make sure our change is working correctly. It looks like everything updated correctly. This completes our work on the user camera for now. In the next video, we're going to start including entities that can move around and interact with our map.